Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi class, welcome to our discussion on the tutorial questions. Now first thing first, I hope you have done and not entirely waiting for the answers, because I am only giving you the written answers only for part of the questions, and the rest I'm just going to discuss. Some is just telling you where you can get the answer. So I do hope that there is you're not solely dependent on the answers, and you make an effort to do this on your own before this discussion. And it's very important, because that will gauge how much you understand, and for things that you feel that you need to look back at your notes, so you have to revise, and so that becomes a revision, indirectly becomes a revision to your quiz and your exam. Okay, let's not waste time. Let's look at the first question. And what I've done, as you can see, I've categorized the questions based on the 10 main topics, so that your thoughts are organized and you follow through what we have actually done. Okay, so what is gyromagnetic ratio? In terms of what it means as a definition, it's because it's a ratio. It means that it's actually a ratio between the magnetic moment to the angular momentum. But when you talk with respect to the NMR spectroscopy, so really what it is, it represents, especially in terms of for the gyromagnetic ratio, which is unique to each nuclear spin, it actually represents its response towards the magnetic field. And as you can see, when there is an applied magnetic field, and in the Zeeman equation, you can see that everything else is constant, but then it all boils down to the gyromagnetic ratio. So second question, why is proton NMR the most common NMR spectroscopy? Well, definitely because it's the most abundant nuclei, and the fact that it has the largest gyromagnetic ratio, so it makes it, you have a very strong signal there, and so that's why it's the most common NMR spectroscopy. So the advantage of using a 600 megahertz over a 400 megahertz is, of course, because you will have better resolution. And so if there's actually, so you can see somewhat the you will see the defined spectrum. The spectrum looks more defined as of when you compare to a low magnetic field. So what does resonance mean in terms of NMR? So if you have questions on, for example, definition, and if it so happens that that definition has an equation tagged to it, it is advisable for you to actually also not just write the definition, but also write the equation that tags with it. And the equation that tags with it is, of course, you have this, the applied, when you have this the Zeeman equation and so on, and that equates the radio frequency, and so this signifies that the what you call the resonance between what the frequency that you applied and the transition that's allowed based on that. So when the frequency of the precessing nuclear spins corresponds to the frequency of the radio frequency striking the material, so energy is absorbed from that radio frequency. So that's, you can have, your own different, definition for it, and as what I've also explained, So I don't want you to memorize word for word, but just understand that the applied magnetic field, when you put the spin, the nucleus in applied magnetic field, and to have that a large transition, it has to match with the radio frequency that you apply. So if you say that, I know that you understand, and so you will get marks for that. Okay, so sketch the energy diagram of a spin half nucleus, because our focus has been on spin half, which is the proton, in the absence of magnetic field and in the presence of magnetic field. Clearly, this is asking you to sketch the Zeeman splitting diagram, and you can get that easily from this. Okay, so this is when there's no magnetic field, and this is when there's an applied magnetic field. So I'm just going to give you an example. So one of the things that student miss is in terms of writing the details when they actually sketch. So you have to put here that this is the energy, and clearly this is magnetic field, and when there's no magnetic field and magnetic field on, so you want to label what's this. So this is the spin down and spin up, or the alpha and the beta, and what's the value, and of course the Zeeman splitting, and you put the equation there. So as soon as you put this, everything is complete. So you get the marks, that's the given marks. And of course write this equation for Zeeman splitting, and so there you have it. Okay, so in terms of I think there are not many equations for you to memorize, but I do hope that the main equations that you do understand, and where this actually comes from. So we've talked about it. As you can see that these are constant, so it based on the first question, so it boils down to gyromagnetic ratio, which is unique to each nucleus. So what is the resonance frequency of a deuterium in a magnetic field of 7.5 Tesla? So you just have to plug in the equation, another equation, the normal frequency, which is also the resonance frequency. And so there you go, and it's 49.02. So this is an example. So I'm not going to, I don't write it here, I'm just going to discuss the answer here. And some of it, I do want you to dig up, so that you're not students have the tendency to think that these are the questions that will come up. These are things that I feel that you should know, so that it will expedite your revision process. So it's another name for resonance frequency. As I said, it's Larmor frequency. And how can the sensitivity of NMR be increased? So if you actually use a higher magnetic field, so that's going to do that job. What does saturation mean? So when you have the spin up and the spin down being equal, so that's when you have the saturation. So what causes spin precession? This is when we talk about this relaxation process. So remember that the precession happens when you have this spin, the nuclear spin, being exposed to this applied magnetic field. So it doesn't actually, because of this what you call the because of this angular momentum, it's the nucleus angular momentum, so it's actually precessed. It doesn't actually point to it's not like a compass. It will point along the direction of magnetic field. It will actually precess first, and so what causes that is because of that the applied magnetic field, which is applied to the nuclear spin, that makes it spin. But as I've already explained, it doesn't spin, it doesn't precess forever. It has all this thermal movement is going on. So in the end, it will actually what you call relaxed, and it will overall it will actually point in a certain direction, which is along the magnetic field. So then define what is the longitudinal and the transverse relaxation. Well, the longitudinal, as I said, that long, so it is actually magnetization along the z-axis, and so that's what this as what we see in the spin precession. Okay, eventually it's going to actually relax, and that's going to relax along the magnetic along the z-axis. And so the transverse relaxation, it's when you actually flip the signal to 90 degrees. So really the free induction signal, which results from the magnetization precessing in the xy plane instead of the z plane, will therefore decay away, and so this loss in the xy magnetization is called the transverse relaxation. So this is relaxation along the z-axis, and this is relaxation in the xy plane. So what is the definition of spectral line width? So again, it's in the notes. So you look at the NMR peak and you look at the height of the peak. So half the height is when you start measuring the line width, and that's where, so it is actually the line width at half the height of a spectrum. Now sketch and compare the FIDs and NMR spectra of liquid state versus solid state. So we have discussed that in the liquid state will have a very sharp peak. It has a longer FID, so if it decays a longer time, and then it has a very sharp peak. In comparison, the solid state usually has a short FID, and it will have a shorter and broader peak. So it's the line width is broader. So yeah, so this is something that you want to sketch, and so the example I give you was the solid state, unusual solid state with a shoulder and a peak, but it can also be just a simple, but then for a very simple FID, which is very short, it just gives a very broad, what do you call a very broad peak. So let's see here. So you have, if I can scribble here, this is long FID, and this is in comparison, this is and then so this is shorter FID, so this will give a very sharp, or maybe that's not too sharp, so this is give very sharp peak, and this will probably give a very broad peak, like that. Okay, so the chemical shift, what is the effect of an electron withdrawing group? Again, I want you to look up at the notes. When you have electron withdrawing group, here you are actually the shielding, you're taking away all the electrons, and so there's the tendency for the signal to be shielded, so you have this the values. So you have the shielding effect, and so the chemical shift will be larger. Why is TMS a suitable reference for NMR gain? Please look up. There are many reasons there. So this is something that you can look up in the notes. I think I give you many points there. Why NMS is a suitable, TMS is, or tetramethyl silane is a suitable reference for NMR. Okay, write the equation for chemical shift. So this is another equation that I want you to remember, and so that it expedites. So you have the chemical shift. I think I have one example problems that you can actually write. So the chemical shift is in ppm, and then you have it equals to the reference frequency in hertz and over the magnetic field applied, okay, and times 10 to the power of 6. So check that out. Sketch the energy level diagram of an AX system where there's no spin coupling versus when there is spin coupling. I think this was in lecture 6 when I showed you, before I gave you that, all you have to do is just do the n+1 rule. But before that, I showed you an energy diagram of an AX system when there's no spin and when there is spin coupling. So you just have to, study that diagram. Okay, AX, AX2, AX3, A2, AX3 system. So sketch the proton, and usually the A is the shielded. And so you have here, if you have an AX system, so you have this, they are actually, so this is the A, this is X, so A is seeing the X, X is seeing the A. So if this, so this is doublet, so A is seeing the X, so there are 2, so this is n+1, so it becomes 3. X is seeing the A, which is 1, so it becomes n+1, so it becomes 2. So vice versa, you see here A seeing X having 3, so it's n+1, so it's 4 here, and X seeing A is equals 1, it's just A there, so just want a proton. And so so you have here the n+1 rule, so 1 + 1 is 2, so you see 2, and vice versa here. Okay, chemical exchange. In an interconversion process, one group has a chemical shift of 5.2 and the other is 4.0. What is the interconversion rate when it actually coalesces or combine into just a single peak? Now there are 3 equations. So this is the chemical shift equation that that question actually, the question previously actually asked. Okay, there are 3 equations pertaining to this. So first is the time that it takes for the 2 signals to coalesce. Now please remember that this what you call delta nu here, it's the difference in frequency in hertz. Okay, so meaning that you have to convert, and this is actually the chemical shift is in ppm, so you have to convert this to hertz first, not just taking this, minus this, and that's what many students did a mistake. So they just took this minus this and plug it in the equation, whereas that is actually in ppm. You have to convert that. So once you convert that to this value in nu, then you plug in the difference. Once you get the difference, okay, you're only solving the time, but the question was the interconversion rate. So rate is 1 over tau. So 1 over tau, or the reciprocal of tau minus 1, that gives you this value. So in what way is carbon-13 complementary? You know that the signal of carbon-13, I hope you look at, I want you to really look at the video that I shared, and it says that it's just like the way that carbon-13 is like proton NMR is that, you know, if the peaks will also signify the types of what you call the types of hydrogen there is. So if similarly, the carbon-13 will only focus on the peaks of carbon and only related to the types of carbon peaks there are. Okay, the groups that pertains to it. So carbon-13 is complementary, you know, because especially when you can't, especially when you have really superimposed peaks or peaks which are very crowded together and so on, this can actually be good to complement, to affirm the molecular structure that you have. This is really an open question, and if this is an exam question, I really you know, do not like and do not fancy when students actually use the internet to actually get the answer. Now you should be doing some reading on this, you know, because as I said, that this is also part of the class to know, at least you know what are the types of applications out there. Even if you actually look at Google, you need to sort of like write in your own words what are the application. And why limit yourself to MRI? Because that's not the only medical application that's being used. So this is where I really want to see, you know, like how you can actually explain, you know, and it's usually 2 or 3 marks, 2 marks usually, just to see that, you know, how do you actually explain in your own words, you know, based on you know, the brief reading that you read, that you find. Okay, so that's it pretty much. Those are the questions, tutorial questions. Again, of course, this I can ask you anything based on the 10 topics here, and these are the questions that, you know, what I feel that you should know, and I can look at, you know, for any of these parts of the 10 parts, there are various questions that I can ask. So you just have to know the basic. It helps when you know the equations well, and it helps especially you know how to use the equation, and when you have open questions like this, use your own words and write according to your understanding. So yeah, so that's it. So all the best. Okay, right, so till then, Assalamualaikum warahmatullahi wabarakatuh, and take care.